temperature actually. Hi, welcome back. So we're going to continue our discussion again from the last time. So this is part 2 of the question. So we are trying to find the final temperature. Okay, so just for the sake of practice, we're going to iterate this again. So we find that our bulk temperature is actually 55 degrees C, thereabout. And then we are going to evaluate our Reynolds and Prandtl number at that temperature. So let's look for Reynolds number first. So what's our Reynolds number? So we're going to look at 55 degrees C, and we're going to find the density. Okay, density at 55 degrees C. So we're going to do this linear interpolation. It's very annoying, but we'll have to do it. So at 40 degrees C, we'll have density of this much, 60 degrees C temperature, density of this much. So we just do some linear interpolation. Okay, so we'll make a guess. Okay, so what's the density at 55 degrees C? So we start from 40 degrees plus, we're going to have the gradient. What's the gradient? So it is the 983.2 minus 992.2 divide by final minus initial. So, and then you multiply by the temperature difference, 55 minus 40. So this is what linear interpolation is like. I start from here, I take the gradient, and then I try and linearly interpolate the temperature difference here. So, quick calculator. Okay, density at 55 C, okay, equals 992.2 plus 983.2 minus 992.2 divide by 20. Okay, 20. I'm just not going to bother typing out again. So and it times 15, you get 985.45. 985.45, sure. All right. Next, we need viscosity. So we have 0.547, 0.467. So we're just going to take the average of these two values because they are just smack in the middle. 55 degrees C is just smack in the middle. Alright. Viscosity equals to half times 0.467 plus 0.547 times 1e minus 3. So I'm gonna get that right this time. Alright, so let's calculate our Reynolds number. So Reynolds number at 55 degrees C. Okay. So again we'll have rho. And what's the density? Viscosity 0.00507. 0.000507. D 0.5. Okay, this is wrong. Should be here. And look, it looks like it's going to be a turbulent flow. Again, made the mistake. But anyway, let's just try. Let's just continue. Rho mu, rho Vd over mu. Let's check again that number. Okay, so it looks like I'm yet made another mistake. Okay, but never mind. U. So rho mu d over mu. Okay. equals to wow, that's a very, very insanely high Reynolds number. Okay. Oh, yeah, so that's a very high Reynolds number. 194,368. Okay. Well, that's a mistake to be made. But never mind. Let's calculate anyway. So the last video, I think I made a mistake because of accidentally having our Nusselt, our viscosity off by a factor of 1,000. I think that's why I made the mistake. So the flow is actually turbulent. In this case, we will actually need to use not this relation because we are not looking at laminar flow anymore. We'll have to look at this. Okay, well, things didn't go as planned. At least we'll get to see now the turbulent side of things. Okay, so this is actually turbulent flow. Alright, so we'll have to use a different Nusselt number this time. We have to use this equation, 0.5-48. Alright. We'll have to use this equation. So we'll need to have a Fannings friction factor first. So this is just nice within the range because the Reynolds number only goes from 10 to the 6, 2300 to 10 to the 6. So this is 1.94 times 10 to the 5th. Okay. That's the correct Reynolds number. Okay. So it fits within this turbulent flow profile really nicely. Okay. So what is what do you need to calculate? First we need to calculate F. So Fannings friction factor. So I'll just delete these. Okay. So what's the Fannings friction factor? So the F here is 0.25. Okay. Times 0.9790 times ln of the Reynolds number. So I'm just going to have a Reynolds number there, minus 1.64, close bracket, to the power of minus 2. Yep, that's what the correlation says. So what's the Reynolds number here? Equals to rho V D divided by viscosity. Okay, so that's the friction factor. Now we have F, we need a Prandtl number. Prandtl number, mu Cp over K. So the mu is what we have calculated then. Prandtl number equals to viscosity times, okay, so let's put it here, Cp and K. So let's look for Cp. Where is Cp? Oh yeah, Cp is constant, right? So 4180, that's assumed constant, and let's look for the thermal conductivity. So here we just assume it's 645 because 640 and 650, if you take the in between, it's just 645. Okay, 0.645. Alright, let's look for the Prandtl number at the bulk temperature. This one is the bulk temp. And so for Prandtl number, the bulk temp, mu Cp divided by K, 3.285. So let's look Prandtl at the bulk. Prandtl at the bulk equals 3.285. Yep, or 3.286, whatever. Yeah, so Okay, so for fully developed flow region between laminar and turbulent, and for fully turbulent flow, this is the correlation. Where Prandtl is, yes, we are within the range. Reynolds, we are also within the range. So K equals to PRB over PRS to the power of 0.11 for liquids with Prandtl number from 0.05 to 20. So this is where we are. Or let's look at the PRS then. We need a Prandtl number at the surface temperature. Okay, so we'll need properties at 30. Okay, we'll just use the correlations here. We'll go through them one at a time. So mu Cp, where's the mu? At 30 is 0.798. 798 times 1e minus 3. That's mu. Where is Cp? 4180. Divide by thermal conductivity at 30 degrees C. Where's thermal conductivity? Thermal conductivity. There you go. 30 degrees, 614, 0.6145. So 5.428. Okay, 5.428. And we have the Prandtl, okay, PR bulk over PR surface. PR surface equals 3.286. 86 divided by 5.428. So the ratio is as such. Okay, so we are within range. So we have a K of PRB divided PRS to the power of 0.11. So this power of 0.11. This is the big K we are talking about. Alright, looks like we have a friction factor. Okay, we have a friction factor. Okay, this is 0.605. So where's our friction factor? This. So I'm just going to copy and paste it here. Yeah. Alright, so we have our friction factor. We have K and we have the Prandtl number at the bulk. We can calculate our Nusselt number now. So let's calculate our Nusselt number. So what's at the top? Let's separate out into the denominator and numerator. So numerator, denominator. So numerator, what's the numerator? Numerator is K. So let's put K there. Times friction factor over 2. F over 2. What's next? RE, Reynolds minus 1000. Okay. So we look for Reynolds number minus 1000 times Prandtl number. So we look for the bulk temperature Prandtl number. That's the numerator. Denominator 1 plus 12.7. 1 plus 12.7 times F over 2 to the half. So let's look. F over 2 to half times Prandtl number at the bulk temperature to the power of 2 over 3 minus 1. Okay. Denominator is so much. So let's do a check again. Because it looks like a very large, very large number. So 1 plus 12.7 F by 2. Okay, F by 2 to the half. So friction factor over 2 to the half. And L14, which is the Prandtl number to the 2/3 minus 1. Okay. Okay, so let's look at the Nusselt number. Oh, 702. That's a very crazy high Nusselt number. Okay. So, sanity check for us. Can Nusselt numbers really go to that big? So, let's take a look. Nusselt number for turbulent flow range. Okay, so you see Wikipedia. See, a larger Nusselt number corresponds to more active convection, with turbulent flow typically in the 100 to 1000 range. So for turbulent flow, this is a reasonable amount. Okay, so Nusselt number is about 700. Or 702. That's reasonable from Wikipedia anyway. Okay, there you go. So the Nusselt number is 702. Okay, 702, and then we'll calculate our Stanton number now. Equals to NUD divided by Prandtl number divided by the Reynolds number. Okay, so this is our Stanton number, 0.001099. So we'll look for our exponent and the final temperature. Ooh, now that doesn't make sense at all, right? Yeah, it looks as if now our Stanton number has decreased. Okay, but anyway, it's a turbulent flow. So let's look at Nusselt number divided by Prandtl number divided by the Reynolds number. Yeah, it's probably because the Reynolds number is huge. That is why. There's a lot of flow going through. That's why it doesn't cool down so fast. Okay, so we'll go through it again. Final temperature. Now at 51 degrees C. Get a final temp of 51 C. 51 C. So this is the third iteration. Probably just now because made the mistake of the Reynolds number, right? All right. So we can do it again. Let's iterate. Okay, so we'll look for our Reynolds number at 51 degrees. Let's take a look. Temp equals to 80 plus 51 divided by 2. Okay, so this is iteration number 3. 80 plus 51. That divided by 2. 65.5. 65.5 degrees C. And now we'll look for our Prandtl number and Reynolds number. So let's look at our Reynolds number again, which kind of shouldn't change much, right? Okay, let's look for... Okay, density shouldn't change much. So the only significant change is viscosity. I can almost guarantee it's going to be turbulent. So what's the temperature we're looking for? 65 degrees C. Alright, let's look for 65 then. 65 is somewhere here, so 0.43. I'll just give and take 0.43. I'm not going to calculate so much again. So 0.43 e minus 3. Okay. And what is that? I'll calculate the 0.43 times 10 to the minus 3. Okay, in SI units. We're going to look for our density, which shouldn't change much as usual. So we'll use our old maybe 975. And yeah, no, not 975. Maybe 978. Okay. Alright, I think I better calculate it properly. Rho equals to 983 plus 983 minus 971.8 minus 983.2 divided by 20 times 15. Or 15. Okay, right. 80 minus 65.5. Okay. 93 plus 971.8 minus 93.2 divided by 20 plus 80 minus 65.5. Okay, 996.9. Other way around. Negative sign change. Hold on, so fishy. This is so fishy. I'm getting weirded up. 971.8. Oh, I think I found a mistake. It should be 97. Oh, now I see, now I see. This is a multiplication. Okay, good. So this is the new Reynolds number. 2.26 times 10 to the 5. So this is, what, 974. I'm just going to leave it there. Reynolds number 2.266 times 10 to the power of 5. Right, this is 10 to the power of 5. Let's put it in scientific. There you go. 2.27, 10 to the 5. Good enough. Alright, we have our Reynolds number and then now Prandtl number. Yeah, calculate our Prandtl number again. The bulk and surface. Surface is going to be the same. It's just the bulk's going to change. So, Prandtl number. What do we need? Not this help. Prandtl number. So Cp is the same, we just need to find the thermal conductivity. So let's look at thermal conductivity at about 65. So that's about 655. Let's do 655, yeah? 0.655. And then our K values become this. Our Nusselt number becomes this. And the Stanton number becomes all of that. Alright, let's do it one at a time. So we find our Prandtl number, our new Prandtl number at the bulk is 2.74. 2.74. So the K value, 2.744. So we are within the correct ratio. 0.5055. So you see the ratio that we need is 0.05 to 20. So 0.5 is about there. So we have our K value. Our K value is, because of Excel, thankfully, we have 0.9277. So that's in. So that becomes our new Prandtl number. Now, our Nusselt number, let's check whether we need to change anything new. Our Nusselt number is considered by changing the friction factor, and the friction factor has changed because of the Excel formula, which is good. Okay, friction factor has changed because of the Excel formula, and now the Reynolds number has changed. Excel has taken that into account, Prandtl as well. So these all have changed. So the Nusselt number is 714. Again, reasonable for turbulent flow. Stanton number didn't change too much. Final temperature is about 49 degrees to 50 degrees. Okay, so I'm just going to copy all this down. This Excel, because it's getting very long. I hope you get the idea of how to calculate now. Final temp, 49.95 degrees C. Now, if you look at this final temp and the last temperature, what's the last temperature? I think it's 51 degrees, right? Where is that last temperature? There you go. See, we get a final temp of 51 degrees C just now. So yeah, we have a final temp of about 50 degrees C, which isn't too far from 51 degrees C. So we can say safely, that our final temp is about 50 degrees C. Okay, so problem solved. So hope this gives you a flavor of what using these correlations is like. It can get a bit frustrating at times, but yeah, other than that, it's pretty okay to use. So this is what solving these kind of problems is actually like. I thank you for your patience if you actually stayed all the way through all 30 minutes of this video. So thank you, I'll see you guys next time.